proportional odds model. As I just talked about previously, we can use the latent variable approach again to derive the proportional odds model, or this most popular autoregression model. So let's say we have this auto response variable, right? That's measured on a 4-point scale from 1 to 4, right? 1 denotes strongly disagree, 2 is disagree, 3 is agree, and 4 is strongly agree. Corresponding to this observed ordinal variable, we have a latent unobserved continuous variable. Okay? So for this continuous variable to be from negative infinity to tau 1, so tau 1 is what is called cut point or threshold, we observe strongly disagree. If y star, this latent unobserved continuous variable, is from tau 1 to tau 2, we observe 2 for this observed ordinal variable, that is disagree. From tau 2 to tau 3, we observe 3. And for the y greater than tau 3, we observe 4 for this observed ordinal variable. And here we have a graph to show two scenarios. In the above is when we could observe this quote-unquote unobserved latent variable. How does the graph look like, right? So we have x-axis, we have y-axis, right? And y-axis corresponds to y star. And we have tau 1, tau 2, and tau 3. And here's scatter plot and regression line here. Okay? And all these data points, right? So for the data points, let's say, appearing below tau 1, we observe y equal to 1. Okay? For the data points appearing between tau 1 and tau 2 for y star, we observe y2, then y3 and y4, etc. But in reality, we don't see that. What we see is, well, here's an x variable, right? Here's a y observed variable, right? 1, 2, 3, 4, 5. What we observe is, 1, right? We have a bar here. We don't have anything in between 0 and 1 because, we don't have those values for the observed y. So we have a couple bars here corresponding to the response levels of y. So this is y, observed y. This is not y star. Y star is this unobserved hypothetical latent continuous variable. Okay? And to do a little bit of translation, basically, what we say is that we have this structural equation, y star, right? Y star here and x here. And without loss of generality, we can assume y star is equal to x beta plus epsilon. And we see y equal to m, that is observed y equal to m, when y star is between tau m minus 1 and tau m. So if y equal to 2, then y star is between tau 1 and tau 2. And if we flip back, we will see that, right? When y star is equal to 2, when y is equal to 2, y star is between tau 1 and tau 2. Okay? Okay. And, well, for each, so here is a graphical presentation of the relationship here. So again, this is a single x here. Xi, xj, xk correspond to specific x values. And here, the y-axis on the left corresponds to y star, the latent unobserved y star, and this is y, observed y. So let's say from tau m minus 1 to tau m. So for any y star falls in this region, okay, fall in this region. Then we'll observe y equal to m, right? Y equal to m. That's what we observe. And the problem is we don't know, actually. We don't know where y star falls, and we don't know how many either. So how to figure that out? Well, we assume there's a probability distribution here. We assume there's a probability distribution here. So for every x value here, we assume there's a conditional distribution y star. And probably you would guess, well, the distribution very much looks like a normal distribution. Well, if it follows a normal distribution, then we can calculate somehow with some assumptions the area under curve, right? So the gray area, the shaded area, actually corresponds to the conditional probability that y equal to n for different axes. Okay, if this appears kind of daunting, let's move on to textual derivation. So what we want to know in this case is the probability of y equal to n given x, right? So m is any response level of this ordinal measure. And people want to know, why do we want to know the probability of y equal to m? Well, because the probabilities that we're talking about, excuse me, the models where we're talking about here are called probability models. And the general strategy is we want to figure out individual probabilities. It's given x, what's the probability of y equal to its observed response value? Okay, once we figure out that equation, what we're going to do, we're going to multiply through and construct what is called a likelihood function. And what's next? Yeah, you would probably guess we're going to apply the maximal likelihood estimation. That is, since we can express the likelihood of observing data as a product of all these individual probabilities, which again are functions of x and beta, then we can use calculus, right, to figure out a solution. Okay, so that's the general idea. If you get lost, that's fine. Let me walk you through. So let me bring back to this individual probability. That is given x, what's the probability of y equal to a certain ordinal response? Okay, according to our assumption, right, the probability of y equal to m is when y star between tau m minus 1 and tau m, right? Okay, well, that's basically, simple application of one of the assumptions, right? Then what is y star? Well, we substitute y star with x beta plus epsilon. Again, that's assumption. That's assumption. Okay? What we're going to do next is we're going to rearrange the equation, right? Move x beta around, right? And we get this equation, this inequality. And this inequality, if you remember basic statistics, okay, then, well, let's say the error term follows certain distribution. Well, better to be a symmetrical distribution. Then the probability for this epsilon, right? So this epsilon follows a certain distribution, right? And for this random variable to fall between two numbers, how to calculate the probability? Well, it corresponds to the area under the curve. How to figure out the area under the curve? Well, we apply that probability, right? So we first calculate the probability from net infinity to tau m minus x beta. Okay, right? So that includes all the dotted area and the shaded area, right? Then we figure out the probability tau m minus 1 minus x beta, right? So this point, okay? And, if this it's called var epsilon, okay, follows any known distribution, then we can figure out probability, right? So how to do that? It's the bigger area, right? The dotted area plus the shaded area minus the dotted area. And that's exactly what this equation is. And to kind of formalize notation, we use F. Okay, so this F denotes this one, and this F denotes that one. Well, this is just the individual probability, right? For a single case, given X, what's the probability of Y equal to N? How about all data points? Or how about all data points? Okay, so for every data points, we have this equation, right? What we're going to do, what's the likelihood function? Well, what is likelihood? Likelihood is the kind of quasi-probability of observing the data, right? And assuming all the data points are IID, that is identically independently distributed, okay? Then we're going to do, we multiply through. So this is multiplication sign, okay, pi, right? That is what we're going to do for all the terms, from I equal to 1 to n, that is, index for observation. We're going to multiply through all the individual probabilities. And then what's next? I think I already talked about that. And also you can watch my lecture on maximum likelihood estimation. Basically, next step is to apply maximum likelihood estimation and figure out the parameter estimates and their associated precision estimates. Okay, and how about the distribution of error terms, right? I just talked about, if we could assume some distribution or error term. Well, it either follow a standard normal, it's called standard normal, with mean 0, standard deviation 1, and when that assumption holds, we have what is called ordered probing model. Okay, ordered probing model. Well, if the error term follows what is called standard logistic distribution, okay, with mean of 0 and the variance pi square is equal to pi square over 3, then when you say, well, it follows this is an ordered logit model. Okay, so depending upon the distribution assumptions we make about the error term in the structural equation we have, that's actually an assumption 2, right? Same error, okay, here. Then we can have either order probit or order logit models.